giving this first talk at this meeting, and very many thanks for inviting me. I better ask first, am I clear? Can you hear me well?
Yes, we can hear you.
You can hear me well, okay. So, my talk's titled Some Remarks on the Complex Exponential Field.
Sorry.
Yeah.
Professor Wilkie, no, before you were started, I'm sorry. It's the director of Fields Institute that it's going to say some words. I'm sorry.
Oh, I'm sorry. I thought you were talking to me.
Okay.
Okay, so may I begin? Hello, everyone. Welcome to the Fields Institute. And yes, we were all eager to hear Professor Wilkie's talk, and so I was also listening to what he was starting to say. but it is my honor and privilege as director of the Institute to welcome groups of researchers at the beginning of a workshop or a conference or a program. We're having this thematic program on Tame series, and it's going, I think, really well. I see a lot of activity during the term. We're probably in the final stretch, maybe the final month of the program. So congratulate all of the organizers for organizing a really good set of events. This workshop being I think the third and perhaps final workshop of the program. Many of you may be familiar with the Fields Institute, but briefly for those who are not, we're a research institute, independent organization. We have about 20 universities as members, as principal sponsoring universities or affiliated universities. We are funded by the federal government through the Natural Sciences and Engineering Research Council, to the Canadian Institute of Health Research, and also through the Social Sciences and Humanities Research Council. We're funded also by the province of Ontario, as well as several foundations, including the National Science Foundation and the Science Foundation of America, and also by individual donors, generous people who support the mission of the Institute. The goal of the Institute is to make it possible for people to meet together and share ideas, share insights, so that it sparks further collaboration and cooperation. For the last 2 years, of course, we've been doing this in this first purely online and now hybrid mode. And I congratulate all of you, all organizers, participants, and staff also for making it as seamless and as painless as possible. I think it has maybe not as optimal as meeting entirely in person, but nevertheless has been very, very fruitful. And I'm hopefully it'll continue in that way. So once again, welcome. If you hear, by the way, those background noises are the constant stream of emails that I get. I don't know how to turn those off, sorry. I wish you a very, very productive workshop where you enjoy each other's company and talk to each other and prove lots of new theorems. One request I have is when you prove your fantastic new theorem and submit your paper to the Annals of Mathematics, please do thank the Fields Institute for providing the environment for you to do your fantastic research. Once again, welcome to the Institute, welcome to the workshop, and I hand it over now to the organizers and perhaps to Professor Wilkie.
Thank you, Director Murthy.
It's my very great pleasure to introduce the first speaker this morning, Alex Wilkie. The suggested title is Some Remarks on the Complex Exponential Field, so I think we'll go with that. Thank you.
Yes, thanks very much. I didn't know that was there. Yeah. Again, sorry for interrupting at the beginning. And very many thanks for inviting me, especially to give the first talk. And I hope it all goes through okay. So that is the title, and the complex exponential field is that structure, CX. So it's the complex numbers with the ring operations and the full exponential function, e to the z. And Zilber first considered studying this. I mean, it seemed shocking at the time, because, as we all know, the ring of integers is definable in this structure. And that usually means an end to any kind of reasonable model theory, because you have all what we call the Gödel phenomena. It makes it undecidable. But then Silber said, well, maybe that's all that happens. Maybe this is really is a tame structure. You just have to accept the sets definable in the integers, and maybe there's not much else happens. Maybe we can have some theory of the definable sets, possibly modulo countable sets, something like that. And he indeed conjectured that this structure is what is called quasi-minimal. And in fact, even for the logic L omega 1 omega, where countable conjunctions and disjunctions are allowed, and this just means that every subset of the complex numbers themselves that's definable here, as I say, even in L omega 1 omega, is either countable or its complement is countable. So it's either countable or co-countable. And of course, that's all you can hope for, as the integers themselves are definable. And this attracted me very much. I've been working on and off on this problem for well over 20 years. And I'd like to tell you about my approach to it. First of all, Silber's approach is as follows. First of all, let me define an EA function. By an EA function, I simply mean a polynomial with complex coefficients in, say, n variables, z1 up to zn, and they're exponentials. Okay, so a sort of exponential polynomial. That's all I mean by an exponential algebraic function. And then Silber wrote down this axiom B. It's a single axiom in a certain infinitary language, which I'll mention in a minute. Well, first of all, you write down the obvious ones, just the axioms for algebraically closed fields as a field, and the obvious laws of exponentiation. Then you write down what's called the Chaniel property, which we'll hear about in the next talk. So I won't say too much about it, but it's saying there can be no overdetermined complex numbers as far as EA functions go. In other words, you cannot have a solution to n+1 equations and n unknowns non-singularly. Yeah, that's basically it, plus a slight variation on that, but I don't want to say anything about that. Now, thirdly, Silber's axioms that correspond in just the field case to closure, to algebraic closure. So this is what we call exponential algebraic closure, which says that if we take any EA map, that's just an n tuple of EA functions, from Cn to Cn, they have a zero, provided that this is not ruled out by axioms 1 and 2, providing it wouldn't give you, say, a counterexample to Chaniel's conjecture. Those are his axioms. And he proved that B, this is it's actually a sentence in the infinitary language L omega 1 omega with a quantifier for there exists countably many, or uncountably many, it's usually phrased as. So this axiom has a unique model in each uncountable cardinality. So in particular, it's consistent, which is certainly not completely obvious when you start looking at them. It has a unique model in each uncountable cardinality. And further, this model is quasi-minimal. Every definable subset of the complex numbers is either countable or co-countable. In particular, if we knew that Cx actually satisfied these axioms, then Cx would be quasi-minimal. Now, Bayes and Kirby have actually reduced this assumption, for at least for quasi-minimality. It's actually sufficient that Cx satisfies the third class of axioms. You don't need to know anything about what's called Chaniel's conjecture. And that implies quasi-minimality. But even so, as I said, I want to go on to my approach to this problem. Even so, you have to find points on EA varieties to try and show that CX satisfies this axiom. Part of the problem here is that in the algebraic case, you can reduce to one variable functions. I mean, a field is algebraically closed if and only if every polynomial in one variable over the field has a root. But here you can't do that when you have the exponential function. You have to consider maps. You have to consider functions in n variables. And finding points on these varieties does seem difficult, though many people have solved special cases of it. But the trouble is sometimes you have to assume this Chaniol property in order to get the points. But anyway, now I'm proposing another conjecture, still a conjecture, which implies quasi-minimality, where you don't actually have to find points on varieties. You start with a point, and you suppose there's another parameter z in your equations, and we ask for an analytic continuation of this solution, this point on the variety, as the parameter z varies, at least as it varies generically. So what does generic mean? Well, generic means generic in a certain pre-geometry, and this pre-geometry was inspired, well, a long time ago in the real case by work of Hovansky, his work on few nomials, and indeed on the real exponential function. And so we say that a zero A bar, an n tuple A bar of a EA map phi, which is just an n tuple of EA functions, mapping C to the n to C to the n, we say it's non-singular if the Jacobian of that system, which is just the determinant of the matrix of partial derivatives, so that's a square matrix, n by n, if that does not vanish. Okay, it's the usual definition, I think, of a non-singular zero of a system. Note, by the way, that this determinant is an EA function itself. You only get another EA polynomial, an exponential polynomial. Okay, so that's what a non-singular zero of a system is. And then we introduce this closure operation on subsets of the complex numbers. So if we take any set S of complex numbers, then its EA closure is a little complicated to start with, but I'll go through it slowly. Denoted EAS, it consists of precisely those complex numbers B that lie in an n tuple of a non-singular solution to an EA map. Okay, so as I said, you have to take functions in many variables. You can't just do this with functions in one variable, like in the algebraic case. So it consists precisely of those complex numbers B, such that for some n and some EA map phi, from C to the n to C to the n, with coefficients in the field generated by S. Oh, by the coefficients, of course, I just mean the coefficients of the polynomials that define the polynomials in the map. So some EA map defined over Q of S and some non-singular zero A bar of phi, we have B is amongst the coordinates, say the first coordinate. Okay, so you take all EA maps, you look at all the non-singular solutions and all the coordinates thereof, and you put them all together, and that's it. That's the EA closure. And that's going to be what our substitute for algebraic closure in the exponential case. And then based on the proof I gave in the real case, which was really based on the work of Hovansky, it's fairly easy to show this is a pre-geometry on C. It's a closure operation, and it satisfies the exchange rule. If A is in the closure of B, and A is not in the closure of the empty set, then B is in the closure of A. Okay, now, so here comes the conjecture. So let's talk about analytic continuations of EA solutions. Suppose that I'm given an EA map in 1 plus n variables. So I distinguish the first variable as Z0, and then we have Z1 up to Zn. And so I just write phi sub z naught of z bar for phi z bar z naught z bar. But it's important that this function just depends, well, it can even depend just polynomially on z naught for this definition. So let's fix a complex number omega. And suppose we take a non-singular zero a bar of the system phi sub omega. Okay, so if we just plug omega in for z naught, we're left with a map from c to the n to c to the n. And suppose a bar is a non-singular zero of that map. Then by, as is well known, the implicit function theorem, we can find a small neighborhood of omega, an open neighborhood, say an open disk around omega, and an analytic, complex analytic map from that neighborhood to c to the n. So that's just n complex analytic functions defined on U, such that f of omega is the zero you first thought of, and such that for all z in U, f of z is a solution to phi sub z, f of z equals 0. And you can suppose a non-singular solution, this f of z. Okay, that's just the implicit function theorem. And my analytic continuation conjecture, which I'll call ACC, is simply that such a solution can be continued unless there's an obvious reason why it can't be. Now, that is explained here. So suppose we're given a countable subset of the complex numbers, and suppose that phi is defined over Q of S. In other words, it's a load of polynomials in the zi's and e to the zi's with coefficients in Q of S, the field generated by S. Now, suppose we're given a S generic, and let's just say a linear path starting at omega. So just a function from the real interval 0, 1 into the complex numbers, which is just linear. It just defines a line in the complex numbers from row 0 to row 1. And it's generic, what I call S generic, which just means according to the pre-geometry I've just explained. So in other words, for each t, row of t does not lie in the exponential algebraic closure of S. Now, because S is countable, EA of S is countable as well. Yeah, perhaps I should have said an EA map can only have countably many non-singular solutions. So this is countable. So almost all but countably many lines starting at omega will in fact miss this set. So there's plenty of these S generic linear paths. And the conjecture is that F can be analytically continued along row. Okay, this function that's in a small neighborhood of, defined in a small neighborhood of omega can be continued along any path, even if it goes to infinity, emanating from omega. And in which case, and this is the important thing, of course, because of the preservation, what's it called, preservation of relations, analytic relations, when we continue, everything we get will satisfy the original system. So in other words, phi of row t, f of row t will be 0 non-singularly. Non-singularly because it's a generic path, and the Jacobian didn't vanish at omega, so it can't vanish anywhere along the path at a solution. Okay, so we have this analytic property that's in U, so it must continue to any, whenever the F can be analytically continued, we must still have this relation holding. Okay, so it's then easy to show that if from this, if you assume this conjecture, then it follows actually pretty easily that if you take any two generic complex numbers, okay, so just two complex numbers, generic over S, I should have said. So any two complex numbers not in EA of S, then the exponential algebraic closure of omega 1 will be isomorphic over S to the exponential algebraic closure of omega 2 via some piecewise linear generic path joining omega 1 to omega 2. So as you pass along the path, you'll always get an isomorphic closure. I say piecewise linear here because even though omega 1 and omega 2 are generic, the line joining them might have a generic, non-generic point on it. But if you allow yourself two pieces, you'll always be able to find a two-piece continuous piecewise linear generic path just by a cardinality argument. So any two generic points have this property, and then you can do a natural back and forth argument. Well, these yellow blobs mean that I have to say something else. So the theorem is that assuming the analytic continuation conjecture, if you take any countable set of complex numbers, then any two EA generics over S satisfy exactly the same L infinity omega even S type. In other words, well, if you don't like these infinitary languages, any two generics, omega 1 and omega 2, satisfy exactly the same formulas of the language of this structure with parameters in S. Okay, and that implies immediately that CX is quasi-minimal, because another way of saying this is that if one generic satisfies a certain formula, then all generics do. So, and they are a co-countable set. The set of non-generics is countable. So, a definable set will either contain every generic or none of them. And so that CX would be quasi-minimal. Okay, this back and forth argument, I mean, why not just make this your hypothesis? This EA omega 1 is isomorphic to EA omega 2. I realize I'm pointing at these formulas, and that is not, you can't see that. So I'll just get my pen out. So you might think that just this formula here is enough to guarantee a back and forth argument or some generalization of it. But of course, the problem is when you choose a new point here to try and get the isomorphism to continue, that's the essence of the back and forth argument, you sort of pass over to here, and you may have moved the first point you thought of. But the point about the analytic continuation along a path is that that doesn't happen. The old points you have here stay fixed in the continuation. Even when you remove them and start again, they won't move. So that's essentially the proof of this. Can someone tell me that they're still hearing me? It's slightly. Hello?
Yes, I'm hearing you.
Okay, good. It's very old experience. I only ever done this once before. So.
We're not seeing any movement of your pen, though.
Oh, didn't you see me right there?
I could not. I see that, but that's it.
Yeah, that's.
Was that it?
No, I mean it was a joke. I realized that just pointing at the screen is no good. But
okay.
That's why I got my pen. Yeah, I should tell you the last time I gave one of these talks, or the only other time, was actually to the Malayan Logic Society, and I thought I got everything set up, and then halfway through, I ran out of charge on the iPad, and I had to rush around to find the charger. So anyway, but I'm all right, 59%, right? Okay, we should do it. Okay, so how are we doing for time? About halfway through, I guess. Right, okay, so I just want to try and explain, well, a few ideas about trying to do this analytic continuation of these solutions. And they'll lead us, well, I just have some vaguely random thoughts that have conjectures about various things that I'll explain. Okay, so so here we have U. Okay, here, this open disk in which our function f, implicitly defined function f, is defined and has its center at omega-1. And we start trying to analytically continue along this path. So we're given this generic path from omega-1 to omega-2. And we start at the point on the boundary of this disk and hope that f is defined there and draw a small disk around it, again using the implicit function theorem, around this point T1 to get a small disk. And well, this is just the usual way of analytically continuing. So you take the next point on the boundary of the disk and try and use the implicit function theorem and keep going. So that's explained here. So we continue f of z as far as we can. Here so what I'm doing, I let Rj be the radius of these small disks here. So Rg is the maximal, such that, say, the norm of f of z, remember this is an n-tuple of analytic functions. The norm of f of z minus f of tj, where I've already constructed gj, is less than or equal to 1. So I make it the largest disk where this doesn't increase by more than 1 in norm. Doesn't matter which norm, really. Well, it's the modulus of d equals 1, but n equals 1, but then you take the maximum of the coordinates. So Rj is such that you can increase Tj by Rj in every direction. Mod z minus Tj is less than or equal to Rj, and the function f stays less than or equal to 1. And then we let Tj plus 1 be the point on the path that's on the boundary of that disk. So with Tj plus 1 minus Tj equal Rj in modulus. Okay. Now, we must have that f of Tj tends to infinity. I should say modulus, I suppose. We must have that mod f Tj tends to infinity as j tends to infinity, because if it had a bounded subsequence, we could take a limit point, and that is necessarily a solution of the original system. And because the point is generic, the Jacobian will not vanish. So it would be a non-singular point. So we can use the implicit function theorem again to continue. So the only obstruction to continuing this function f is that it actually tends to infinity. It's j tends to infinity. And we actually may assume that Tj does tend to omega-2, because if it falls short, we just take the omega-2 to be the new point it tends to. And we want to show we can still continue at omega-2. So we may as well suppose omega-2 is the minimal point on the line where we can't continue. Okay, so I now have several strategies. I've explained one of them now, and if I have time, the other is more local, and we'll come to the end. So this is the one where I mention a tentative look at periodic functions in the context of O-minimal structures. So remember, our phi z naught z bar is an n-tuple of exponential polynomials. So polynomials in zj's and e to the zj's. And so I'm going to write them in terms of their real and imaginary parts. So I just write zj to be xj plus I yj, and then the e to the zj becomes that, e to the xj times cos yj plus I sin yj. And when I do that, I get, see, the yj's here only occur polynomially, and the trigonometric functions there only occur polynomially. So we get a formula that I'll call AT. T is the Z naught here. U1 up to UD and V1 up to VD, with the property that as T moves along the path, we always get a solution to u1 up to ud. So, okay, this A is just the combination of saying the real and imaginary parts of these functions here are 0. And you can combine that, as we're in the reals now, you can combine that by just taking sums of squares, if you like. You get a single real trigonometric exponential polynomial equals 0, which has a solution all the way along the path. So in other words, for all t in omega 1, omega 2, we get a solution to, there is a u1 up to ud, a real solution, such that at of u1 up to ud, sine 2 pi u1 up to sine 2 pi ud. You can eliminate the cosines definably. And that formula will in fact be a formula just in the structure, this one, not this one, but this one here will just be as a formula of the language of the real exponential field. So this is in fact polynomial in the V's here, and it involves polynomials and exponentials in the U's. So it's a formula of the language of the real exponential field, I guess, with parameters for the real and imaginary parts of the elements of S. Okay. Okay, so we get this, but since the solution can't be continued, or let's suppose there's no solution at omega 2, this is false at the point omega 2, when we put omega 2 here, or the real and imaginary parts. This should really be 2 real variables, t, for the real and imaginary parts along the line. Actually, sorry, no, it is only 1 variable. You just parameterize the line and then put the, I guess you need a parameter for the argument of the line. Okay, so so we reduce it to that, but we've still got these sine functions, and the u's are tending to infinity. So this is very non-definable in anything O minimal. But this star is clearly equivalent to just this. All we have to do is say that there are u's in 0, 1 here. So really what I'm doing here is I'm taking the integer parts of the u1 up to ud. So it's really the same as saying there's an integer tuple n bar, such that at of u bar plus n bar sine 2 pi u bar, and the u's are in 0, 1 here, right? Because when I put in the u bar plus n here, it doesn't affect anything. So it's because of the periodicity. So what we're looking at, if I just put vys bar here, I'm now here, equal to this formula here, there is a t on the path. This is slight abuse of notation, but you know what I mean. There is a t on the path, and there is a u bar in 0, 1 to the d, satisfying this. Now, that now is a formula of, and I've written it here, it's a formula of the language of the real exponential field where we add the restricted sine function, and that is O minimal. That's an O minimal structure with nice properties. But the trouble is we have to quantify, to get anywhere here, we have to quantify over integers. So the point is that, so let's look what happens when y moves along the path. So when y moves from omega 1 to omega 2, we obtain a chain of lattice points, nj, each one, well, it might be the same lattice point as you move along. We're looking at the imaginary parts of these u's, but it can increase by at most 1, because the modulus does, corresponding to these points I explained before, that I defined before. And then as t moves, we get that this formula is satisfied at the tj's with the nj here. Okay, but for no tuple of natural numbers is it satisfied at omega 2. There's, okay, so that's actually, now there's a subtle point here. We've moved from a continuous map defined by piecing together the implicit functions to just the pure existence here of a solution. So I'm sacrificing the continuity of the solution for just looking at solutions possibly on different connected components of the original variety. But anyway, so that's what's happening here. So we have a no minimal definable set with lots of integer points on it. In fact, a whole chain of integer points. Now, does this force omega mod of omega 2 minus omega 1, so the length of the path, actually omega 1 I should have taken to be 0 at the first place. It can always taken to be definable because we just move the original omega 1 to say a Gaussian rational or something in the set U. Anyway, does having lots of integer points force the endpoint at which there are any to be actually definable? And well, yes, obviously definable. I mean 0 definable in this structure, definable just from S. Now, that's not totally satisfactory, even if that were true, because it wouldn't force omega 2 itself as two real numbers to be definable. But it would show that the set of Z noughts, which are a projection of this variety, has a piecewise real analytic boundary, because generically it's the modulus of the points on the boundary are definable. And there's various compactness things you can do to show that as you vary the argument of the line that we had to start with, let's go back here. As you vary this line slightly, the angle, we get a real analytic path here. And that would be incredibly useful information, because we know across analytic paths, there are all sorts of tricks you can do, like Schwarz reflection to continue functions. So that's the best we're at. That's the best we can do, but I'm feeling that might be sufficient anyway. Anyway, so that's the plan. So let me come to this question about O-minimal sets that contain a whole chain of integer points, or lots of integer points. Now, if the set is of lower dimension than the ambient space, which it's not here, but if it were, then we could use various point counting theorems to get what we wanted. You could, a chain of points, you see, for each H, there are, well, at least H points of height H, and that's well good enough for the point counting theorem of myself and Jonathan Peeler, and we get the result. But unfortunately, this is an open set, so I'm really asking about open sets definable in O-minimal structures that contain lots of lattice points. So here's the problem. Suppose that we have a 0 definable set in R to the D in some O-minimal expansion of the real field, depending on a parameter X. And so I want to know, is containing a large part of a chain a definable property of X? So for example, what if you draw a few patterns in low dimensions? It seems highly plausible that does this containing a chain here, the thing in inverted commas, for example, imply that either Vx contains large parts of a rational linear subspace, in other words, the integer points are linearly rationally related, or else a large cube, a cube of large size. Now, if you just think in 2 dimensions and you have a lattice chain going through your open set, then suppose that for some n, there are no straight lines of length n in it, then the thing is behaving a bit like random motion. It's kind of has to keep going up and down, up and down. Now, how could the original set, given that it's definable in no minimal structure, not contain a large square? Because if you just look at the bounding points there, they're sort of varying by integers and not in any linear fashion. It almost seems unimaginable that the O minimal set couldn't contain a large square. Well, in fact, 2 dimensions, it is true. But when you get onto higher dimensions, it still looks very true, but geometrically. But anyway, can't quite prove that yet. Otherwise, I'd be telling you. Another way of looking at it, or I'm now drifting a little away from the original problem, but they are things that occurred to me, might be interesting for people to think about. Suppose I take a maximal open interval contained in those parameters x, such that the set does contain a lattice point. So I have an O minimal set or collection of sets depending on a real parameter. And I'm asking for which x does the fiber contain a lattice point? Now, that will be, well, let's suppose Vx and the projection is open. That will be a countable union of intervals. That's this set. Now, must the endpoints, I'm asking, is this true? I'm not saying this is a theorem. Then should the endpoints be 0 definable? So in other words, can you tell when you've got an integer lattice point on your variety, you suddenly move a little way to the right, and then suddenly all lattice points disappear? Now, it seems if you think about cell decomposition, it almost means that one of the cell boundaries takes an integer, has an integer lattice point on it. And that's, again, something for the point counting theorem. But that really is only a good argument in low dimensions. So let me give you an example just in the real field. So d equals 1, this is easy. But for d equals 2, what's the nature of this set? The set of reals for which there are 2 integers n and m, such that x has this fantastically good approximation, nx minus m is less than 1 over n squared. Now notice I'm not asking for there to be arbitrary large n and x such that this holds for x, just 1. And you think, well, okay, you just go up to the x where this is an equality, and that surely is the endpoint of one of the intervals. But there may be much larger n and m such that you have a good approximation at that particular x, and you go on, and there might still be larger and larger ones. In fact, I don't think that can happen in this case, but it's an arithmetical argument rather than no minimal one. But then we can go on, and I was getting a bit fanciful now. I hope you don't mind as we're getting towards the end. In general, what can we say about O minimal structures expanded by a predicate for the integers? Now, of course, nothing. Even for the real field expanded by the integers, we can say absolutely nothing because it's equivalent to what's called second order arithmetic. But then it occurred to me, usually we can work in the minimal model of our own minimal structures for a lot of this. So what about the algebraic numbers with a predicate for the integers? Now, perhaps someone knows about that. It seems someone ought to have thought about that, but I don't know. So I take the real algebraics and just the O minimal structure with that domain, just the ring, ordered ring, or perhaps the minimal model of an arbitrary O minimal structure, and I add the integers. Now, this vastly differs from this because the theory of this is logically impossible. It's almost like set theory, whereas this is purely arithmetical. Well, it's hyper-arithmetic, the complexity of the theory. So this is logically much less complex than this. So, and for again, it's easy to show that the subsets of Z that are definable here are just the arithmetic sets, the subsets that are definable in the ring of integers. I mean, they are complicated, but we can I don't mind taking those as given. There's a nice Roths theorem is a theorem here, and I'm wondering if these types of theorems would axiomatize this structure. So here's Roths theorem, which is true for all numbers x here, because it's true for all algebraic numbers, namely for all non-rational x, that's rational with respect to that z, of course, and for any given positive integer p, there has to be a point beyond which you can't approximate x to within that. That's Roth's theorem. And that is a first order statement that's true in this structure. And I just wonder if you do write down this and all possible instances of Dirichlet's approximation theorems, whether you get an axiomization of this structure. And then I wondered about going back to just the real field with power functions and the predicate 2 to the z. Now, Van den Dries showed that if you don't add any power functions, then that's a reasonably tame structure. And Chris Miller also showed that if you don't have power functions and other than rational power functions, and you just put anything polynomially bounded, no minimal here, it still has a tame, the definable sets are reasonably tame, and you can certainly work with them. And then, well, I thought Philip Hieronymi proved that if you put one irrational power here, then you can construct the integers. Can anyone tell me if that's true? I tried looking it up this morning, and I couldn't then find the paper, but
that's true.
That is true, yeah.
Yes.
Yeah.
I'll look up the reference for you.
Okay, I looked at all what I thought was all these papers, and I couldn't find one with that in. Anyway, so if you have one irrational power here, and the predicate for powers of 2, or anything in fact, then this becomes just as bad as the real field with the integers. It's impossible to study. But then for all this work on complex functions that are closely related to our minimal structures, we only need the existential theory. So I'm wondering, even if we take all a countable field, any countable field here, whether the existential theory of this structure is reasonable, the existentially definable sets. Now, again, I don't know, I'm not sure if anyone has worked on that, but if that's reasonable, then that would be a very good way into what's called the raising of powers problem. So this is a sub-problem of Zilber's conjecture. So I've sort of drifted quite a long way. So I should probably stop there. I had some comments about the local theory, but I don't think I'll, have time. Go away, right. Time for that. So, and some properties of complex functions defined in minimal structures, but I think it's a good place to stop. So if you have been, thanks for listening.
Let's thank the speaker.